Morning class. This is a teacher that the course will be continuing from where we stop on salts. And this morning we'll be talking about water of crystallization. Water of crystallization. You came about water of crystallization when we're doing separation techniques. When I told you that time that there are some salts that you recover by crystallization because they have very low melting point, so they easily decompose when you subject them to evaporation to dryness. So this kind of salts, you recover them by crystallization. And from the word crystal, crystal means substance that has a regular shape. That's crystals. So when you recover a salt by crystallization, that kind of salt will have regular shape, and it's actually purer. It's purer than the salt you obtain by evaporation to dryness. Now, whenever you recover a salt by crystallization, there is a definite or a particular amount of water molecules that they always come out with when they are forming that crystals. This water molecule is definite for each salt, and there are some salts that they don't form water crystallization when they crystallize. There are some salts like that, like sodium chloride salt, potassium chloride salt. But majority of the salts that you recover by crystallization usually come up with a definite amount of water molecule. This definite amount of water molecule that a salt normally combine with when they form crystals from their solution, that is when you crystallize them, you call that water of crystallization. The definite amount of water molecules that some salts usually combine with, when those salt forms are crystals from their solutions, you call that water of crystallization. Like I said before, it's definite for every salt. And I'm going to give you some example of salts now, and the definite amount of water molecules they normally crystallize with. Take note, water crystallization is a definite amount. It is definite, it is particular for a particular salt. When you form a salt by crystallization, they normally come out with a particular water molecule. This amount of water molecule, you call it water of crystallization. Don't forget, I define it here as the amount of water molecule that some substances combine with when they form salt from their aqueous solution. That's a wide definition. So that's a wide definition some years ago. So that's why I put it there for you. So salts that have water crystallization, we call them hydrated salts. Salts that has water crystallization, we call them hydrated salts. So I'm going to be giving you examples of hydrated salts and the amount of water molecules they normally combine with. Examples of those salts are sodium triazosulfate 4. The amount of that molecule that one comes out with is 10. So you say that is decahydrate. If it is 1, that's monohydrate. 2 is dihydrate. 3 is trihydrate. If the water molecule is 4, tetrahydrate. If it is 5, then that will be pentahydrate. If it is 6, hexahedral, like hexagon, decagon, all those gon, whatever. You remember? So if it is 12, that's dodecahydrate. Do you remember alums? Alums are double salt, right? Do you observe that they always have dot 12 of water in front of their formulas? That's a dodecahydrate salt. So you also crystallize them. Now, another example of hydrated salt is iron 2 tetraoxosulfate 6. Right? That one has 7 water molecules. That's heptahydrate. Then sodium trisulcarbonate 4 is called washing soda. Washing soda is the decahydrate form of sodium trisulcarbonate 4. Washing soda. So don't forget about that. So if I say washing soda, I am talking about sodium trisulcarbonate 4 deca. That's 10. Decahydrate. So we also have some other salt like that, like magnesium sulfate. That one too is heptahydrate. That's why I did not write here, like potassium triisonitrate 5. That one is trihydrate. Dihydrates rather. Sorry about that. Then calcium tetrasulfate 6 dihydrates. So don't forget about that. So that calcium sulfate is dihydrates. Why magnesium sulfate is heptahydrates. Very, very important. Now, before I actually come to calculations, I want you to note something. Water molecules normally add shape and color to hydrated salts. Generally, all hydrated salts are crystalline. They have shape. They have particular shape. So it is from water molecules that you get that shape. Don't forget that. That is why if you heat an hydrated salt, it will lose all those water molecules. As it's losing the water molecules, it will lose its shape. It will become powdery. It will become like powder. Don't forget that. It will become like powder. Meaning that it is because of the water molecule that is present that made them have those shape in the first place. So you now discover that when you heat the water, the hydrated salt now, and they lose all their water molecules, they now become powdery. They become amorphous. Amorphous means no shape, shapeless, like amoeba, no shape. So that means that water hydration usually add shape to salt. Apart from that, water crystallization usually add color. They normally add color to hydrated salt. For example, copper sulfate and hydrous. Copper sulfate and hydrous is white. But when you add water to it and you crystallize it, the color will change from white to blue. Meaning that it is because of water molecules that the color turns blue. So meaning that water crystallization, as much as it add shape, it also add color to hydrated salt. You get that? So I just give you an example of copper sulfate now. The anhydrous form of copper sulfate is actually is white, but when you add water, it turns blue, and we use that as test for water. When we get to water, you are going to know. Test for water. Water turns white anhydrous copper sulfate blue. So don't forget that. But I still remember. I will still remind you later about that. Now, let's see calculations that are involved in water or crystallization. Let's take an example there. When 7.7 grams of hydrated salt But we don't know the water of hydration now, but we know that it is hydrated. That is, the salt plus water of crystallization, everything is 7.7 gram. Pay attention. When it was heated, what happened? When you heat an hydrated salt, it will lose all the water molecules, isn't it? You did, right? When you heat it, the water molecule will go. Then they say that the mass after heating it became 4.77 grams. Take note of that. Before you heat it, when it is hydrated, the mass is 7.47. But when you now heat it to a constant mass, that is when you heat it and the mass become constant, then the mass of the anhydrous, that is the one without water, was 4.77. So can you tell me the mass of water that was driven off, and that was heated away? Can you tell me? So definitely it will be 7.47. That was the salt together with water, minus 4.77. This was the salt without water, right? So if you want to know the amount of water that has been driven off, that means subtract this from this, you will get your answer. So that will give you an idea of the mass of water molecules that has been driven off. Now let us see how to solve the question. So the question now tells us that we should calculate the amount of water molecules that was the amount of water of crystallization that was present in the salts. Then you will need all these values during the calculations. Let us see the solution to it. But before we enter the solution, look at the question very well. When the salt was hydrated, when the salt was hydrated, that is when it has water molecules, the mass was 7.47. But when the salt lost its water of hydration, the mass reduced to 4.77. So what you need to get from that place is the amount of water molecules that was actually driven off. You will need it. It's going to be very, very important to your well-being. Now let's see how that thing is being solved. Let's take a look. Let me zoom in for you so that you can see very well. Now these are the parameters that you will need. You will need all these parameters. Sorry about that. You need all these parameters now. Let me put it in. Now you need these parameters. What is the mass of the anhydrous salt? That is the salt when you have driven the water away. The salt when it doesn't have water is 4.77. You remember that? So we know that the mass of the hydrated salt was 7.47. So what was the mass of water that was lost? I told you before, you subtract this from this. Of course, it's reasonable. This one was when it has water. This one was when it doesn't have water. So you know the mass of water that was lost, 2.7 grams. Are we together? Now, what is the molar mass of the anhydrous salt, the salt without water? The molar mass is 160 grams. Pay attention. Very, very important. So these are the three parameters you will of us find. Mass of the anhydrous salt, that's without water. Mass of water lost. Then mass of the molar mass of the anhydrous copper sulfate. So it might not be copper sulfate, it can be any other salt, but you find the molar mass of that salt. Now, once you have all these three parameters handy, you already have it on ground. Then what you need to do is use this formula. The formula that you must not forget is this formula. The formula is 18N. Actually, that 18 is from molar mass of water, H2O. 18N over molar mass of the anhydrous salts is equals to mass of water lost over mass of anhydrous salts. To make it easy for you, see how it is. 18N talks about molar mass of water, right? In a way. Now check, is equals to mass of water lost. Can you see? 18N, mass of water lost, molar mass of anhydrous salt, mass of anhydrous salt. So the formula is very easy to actually know. 18N over molar mass of anhydrous salt is equals to mass of water over mass of anhydrous salt. So water is on top. Water is on top here. Here too water is on top. Molar mass is here. Here too mass is here. Mass of salt is here. Whereby mass of salt is here. So take note of that. So this side now talks about molar mass. This one for water. This one for this anhydrous salt. Why this one now talked about salt? It talks about mass, rather. It talks about mass. This one for the water that was there or whatever. Then this one now for the mass of the anhydrous salt that remained after you have driven the water away. Now, all the parameters are already up. So you now substitute 18N, this 18N, 18N is 18N. This 18N is from here. This is the 18N from here, right? The molar mass of the anhydrous salt is 160. This is the 160 and this is the 160. Now, mass of water that was lost is 2.70 gram, and that's 2.70 gram, right? Then, finally, mass of anhydrous salt. This is mass of anhydrous salt. That's 4.70 gram. So you solve for N. If you cross multiply, I know that SS1 student, you like to be drawing multiplication. So you can multiply that. So 18N times 4.77 equals to 2.7 times 160. Then you calculate for N. So the N is now what? N is now 5. So that's how you do it. So it means that there are 5 water molecules in copper sulfate. So is it monohydrate, decahydrate, pentahydrate, or what? Is pentahydrate. So now see that therefore the formula of the salt is copper sulfate 5 of water. Can you see now? So the water molecule there is 5. That's how you solve that particular question. So I know you understand, but if you don't understand, you can just go rewind a little bit and listen to it. It's a very simple thing to do. So let's see this checkpoint. Checkpoint 7. Checkpoint 7. Explain what is meant by water or crystallization. You remember I said it is the amount of water molecules that salt combine with, or that compounds combine with, when they form salts from the aqueous solution. You have to master that. It's not difficult to know. It will come out in your exam. So when it comes out, be good enough to answer it. When it comes out, be good enough to answer it. Is that okay? All right. Now let's go to number 1B. I'm trying to make this camera small so that it will not encroach. All right. So let's go to number 1B. When 5.0 gram of a compound Y, when 5.0 gram of a compound Y, 5.0 gram of a compound Y was heated to a constant mass. Now, pay attention. 5.0 gram was a compound Y. That means the compound already has a water of crystallization. So when it was heated, now can you see when it was heated? When you heat it, what will happen? It will lose water molecules, right? So when it was heated to a constant mass, 1.8 gram of water vapor was given off. Now take note of this. When you heat 5.0 gram of a compound Y, 1.8 gram of water was given off. That is the water of crystallization that was present. You can see that there's no stereotype manner of asking this question. You were told that 1.8 gram of water vapor was given off. Last question, the one that we solved, you were told that so amount remained. So amount of the salt remained. So you now use sense to know how many water was given off. But in this question now, you were told the mass of the hydrated salt, then you were told how many water was given off. So you don't need to start calculating, but you will still calculate to know what mass of the salt will remain. If the salt was 5.8 gram when there's water of hydration, then after you eat it, 1.8 gram of water was lost. You will still be able to know how many salts, the anhydrous salt, that is the one without water of crystallization, that actually remained. So let's move on. So this mass was given off. So we are to determine the number of water molecules. Determine the number of water crystallization in one molecule of Y if the molar mass is 160. So I've given you all the parameters now. What we need to do now is, what is the mass of anhydrous? So come back to this. It's not here now. So you know what to do now. This is the mass of hydrated, right? This is the mass of water that was given off. Then if you subtract this from this, that will give you the mass of salt that was left. And that salt is actually the anhydrous salt. When salt has lost its water hydration, it becomes anhydrous salt. So if you do like that, you should get 5 minus 1.8. That's supposed to give you 3.2 grams of the anhydrous salt. So now you have all the parameters. Use your formula. Your formula is 18N over molar mass of anhydrous salt equals to mass of water that was given off over mass of the anhydrous salt. So this molar mass of the anhydrous salt is 160. This is 18. That one, the mass of water that was given off is 18. Then what is the mass of the molar mass? What is the mass of the anhydrous salt? That is after you have heated it, which I told you that is 3.2 by subtracting 5 from 1.8. So if you do that, you get answer that makes sense. The compound is okay. We don't know the compound, but when you do it, let me know what your answer will be. Now let's see number 2. When a sample of crystalline salt X was exposed to air, there was a loss in mass. What phenomenon is exhibited in this? I'll still teach you this in the next slide. When salts lose, there are some salts that lose their water crystallization when you heat them, when you expose them to air, not when you heat them. All salts will lose their water hydration when you heat them, but some salts will lose their water hydration when you expose them to air. So this kind of salts, you call them efflorescent salts. When I get there, you are going to see efflorescent salts. So suggest 2 salts that the salt could be. So any salt that contains water of hydration can possibly effloresce. For example, copper sulfate 5 of water, sodium carbonate 10 of water, MgSO4 7 of water, potassium nitrate trihydrate. Once the salt contains water of hydration, there's the possibility of efflorescence. That is, it can lose that water when it's exposed to air. So that is just what is actually happening in this place. So now let's see the calculations here. They said on eating 5 gram sample of X to constant mass, 1.8 gram was lost in form of water vapor. This question B and question this, they're actually Y questions that came out in different years. But if you apply sense, you will see that they actually resemble each other, if put together with number. The only difference was that one was X, one was Y. Then let me see how you would do it. Calculate the number of molecules of water of crystallization in 1 molecule of Y. So you are giving H, you are giving O to be 16, you are giving a hydrous form of X to be 160 gram. So let us see how you do that. Number 3. A 4.3 gram of hydrated sodium sulfate, X of water. So we don't know the water crystallization. They said it was heated. When it was heated, you know what happens. It's going to lose that water of crystallization. Then the remaining hydrous salt had a mass of 2.12. Now you have seen that the mass left was 2.12. So you need to use brain and sense to calculate, to determine the mass of water that was driven off, right? So you have to determine the mass of water that was driven off. So you'll be able to do that. You know what to do. You know what to do. So don't let me tell you. So find the value of X in the hydrated sample. Just know what to do. What's the mass of your hydrated? What's the mass of your anhydrous salts? Write it out. That is, you get it by minusing 2.12 from 4.3. Then the mass of water driven off. The mass of water driven off is 4.3 minus 2.12. The mass of the anhydrous salt is already given at 2.12. Then what else do you need? You need the molar mass of the salt. Calculate it from this parameter. Molar mass of the anhydrous salt, that is salt without water crystallization. That is salt without water crystallization. Please, the salt is Na2SO4. Not NaSO. I'm sorry for that. I think my PowerPoint is having an issue. The salt is Na2SO4. Please, so that when calculating molar mass, you will know. Please, is Na2SO4. So find the molar mass of the anhydrous salt. So let me hear from you. What is your answer? What is your answer in that particular place? Finally, somebody say finally. What are the characteristics of salt? There are 3 kinds of salts which we are going to see here now. 3 of them. We have efflorescence, we have deliquescence, and we have hygroscopic. Efflorescence, I was trying to explain it the other time, but I'll go deeper now. Deliquescence and hygroscopy. Now, let's move to efflorescence. I told you the other time that there are some salts that when you expose them to atmosphere, they lose their water crystallization to the atmosphere. They lose it. They already have it before. When you expose it to the atmosphere, they now lose that water crystallization. This phenomenon is called efflorescence. Now, it can happen that they lose parts and not all. It's also efflorescent too. Either they lose all or they lose parts. Is efflorescence that is occurring. Now, when they lose all the water crystallization, they are going to become anhydrous, shapeless, and colorless, maybe. That's if they lose all. They become anhydrous. They become anhydrous, this anhydrous. If they lose all, they become anhydrous. But if they lose part, they did not lose all. If they lose parts, if they did not lose all, if they lose parts, they become lower dehydrate. That is, for example, now if it's having 15 before and then it's now having 5, that's a lower dehydrate form. So if they lose part, they form lower dehydrate. If they lose all, they form anhydrous salt. Both formation of lower dehydrate or formation of anhydrous salt, they are called efflorescence. So when a salt is exposed to atmosphere and in the process it lost all or part of its water crystallization to the atmosphere, that is called efflorescence. An example of an efflorescent salt is sodium carbonate 10 of water. Can you see that there's 10 of water in this compound? Can you see 10 of water in this compound? 10 of water. But now, see what happened. It has lost 9. It lost 9 out of the 10. It now remains only 1. So that is called efflorescence. That's called efflorescence. If I want to complete now, I'll write 9H2O. That's what it lost. So that's called efflorescence. And this type of salts that undergo efflorescence, you call them efflorescent salt. Efflorescent salt. If you keep exposing this monohydrate form, that's a lower dehydrate. Monohydrate form to air, it can lose all the water molecules, and then what happens is that it's going to form an anhydrous salt. So that's efflorescence. Deliquescence in let me start from hygroscopy. Hygroscopy is a form or is a process. You know, this one is a little bit opposite of efflorescence. These compounds, they don't usually contain water crystallization. When you expose them to atmosphere, they absorb water from atmosphere. They absorb that water from atmosphere. That is called hygroscopy. When substances absorb water or moisture from atmosphere, it's called hygroscopy. When they absorb this water, they can either become, if they are solid, they become sticky or they become wet. That's hygroscopy. So they increase in mass in a sense, they increase in mass because of the water they are absorbing from the atmosphere. So that's called hygroscopy. Hygroscopy. Now, listen very well. When they absorb water from the atmosphere, but they did not dissolve in that water, they did not form a solution, they did not dissolve in that water, you call it hygroscopy. Are we together? They absorb the water from the atmosphere without dissolving in the water. They did not absorb plenty water to dissolve in it. That is called hygroscopy. They just become sticky or become wet, but they don't dissolve in the water. They don't form a solution in the water. That's hygroscopy. So hygroscopy is a phenomenon. That's a big English, Abi. Call it a process. It's a process in which a substance absorbs moisture. Moisture means water in chemistry from the atmosphere and does not form a solution. It absorbs water from the atmosphere without forming a solution. That is called hygroscopy. Example of hygroscopic salt are listed here, and it will be good for your health. It will be good for your health if you actually master this example. They are not plenty and they are not hard. Sodium triethylnitrate 5, that's NaNO3. Potassium nitrate, KNO3. Calcium oxide and copper 2 oxide. They are hygroscopic substances. Now there's something about these hygroscopic substances. Because of their affinity for water, because they can absorb water from the atmosphere, when they are exposed to the atmosphere, they are usually used as drying agents in the laboratory. You can put them inside desiccator. You know the desiccator now. I showed you the diagram in the lab that day. I showed you the apparatus in the lab that day, and you saw where they normally put drying agent under the at the bottom of the instrument. Now, most times it is hygroscopic substance you put it there. because of their affinity for moisture. So they will absorb all the moisture inside the desiccator and provide a dry atmosphere in the desiccator. So that's why you use them as drying agent for drying things in the laboratory. Now, so examples of hygroscopic substance are sodium nitrate, potassium nitrate, calcium oxide, copper 2 oxide. There is one important liquid. My brother, that liquid is an hygroscopic substance, and it's very important for you to know it. The name of the liquid is concentrated tetraoxosulfasis acid, conc H2SO4. It's very hygroscopic. If you expose it to air now, it absorbs water from the atmosphere and dilute itself in the water up to 4 times. That's how hygroscopic H2SO4 is. So it's very, very hygroscopic. Take note of that. Now, don't forget efflorescence salts that you expose to atmosphere and they lose their water of crystallization to the atmosphere. That's efflorescence. But hygroscopic, you expose them to atmosphere and they absorb water from it. Remember, one is losing water, one is gaining water. Efflorescence is losing water to the atmosphere because it has water crystallization, while hygroscopy is doing what? It's actually absorbing water from the atmosphere because it has affinity for water. Now give me an example. Don't forget conc H2SO4 is hygroscopic in nature. Finally, the third characteristic of salt is deliquescence. Deliquescence is almost the same as hygroscopy in that these salts also absorb water from the atmosphere. But the difference is this, take note and be fine. The difference is that they absorb so much water that they dissolve in that water that they absorb. They absorb so much water that they dissolve inside that water that they absorb. Take note of that. It's a process by which a substance absorbs water from the atmosphere, or moisture if you like. Moisture means water. And turn into a solution inside of that. They form a solution inside the water they absorb. So that process in which a substance absorbs moisture from the atmosphere and turn into solution, we call that deliquescence. So the type of salt that undergoes this phenomenon is called deliquescent salt. What do we call it? Deliquescent salt. Salt that when they are exposed to atmosphere, they absorb water and form a solution in it. You call them deliquescent salts. I hope that is correct. That is understood. Now, there are some examples of deliquescent compound. That is not necessarily salt. They are compounds. It will not be so like KOH now. Potassium hydroxide. If you leave it, when you get to school, we'll do practical on this one. We'll leave sodium hydroxide pellets on the window of our laboratory. We'll come back to check it the following day. You see that it has turned to water completely from something like a tablet. It's not the one that normally press. The tablet that normally taken. That's how the pellet looks like. So if you expose it to atmosphere, it will turn to water. It will become watery. It will dissolve in the solution. That is deliquescent. So KOH is a deliquescent salt. Not a salt, rather. KOH is a deliquescent compound. NaOH is also a deliquescent substance. FeCl3 is deliquescent. CaCl2 is deliquescent. MgCl2 is deliquescent. So potassium hydroxide, sodium hydroxide, iron 3 chloride, calcium chloride, and magnesium chloride, they are deliquescent substances. I normally give my students this thing, so it will also be of help to you. I give them POSO. Let me write it somewhere. I give them poso hydroxide. Do you know poso hydroxide? Potassium hydroxide, sodium hydroxide. So potassium hydroxide, sodium hydroxide, poso hydroxide. You observe that all these are chloride. So I call it ficamachloride. Ficammed chloride. So iodine chloride, calcium chloride, magnesium chloride. So ficam chloride. So poso hydroxide, that is potassium hydroxide, sodium hydroxide. Both of them are having hydroxide. So poso hydroxide, ficamachloride. I've already given you 5 examples just by saying poso hydroxide, ficamachloride. So I'm giving you 5 examples now to remember examples of deliquescent salts. Don't forget deliquescent salts. That's the one that absorb water from the atmosphere and dissolve in the water to form a solution. Hygroscopic, on the other hand, they also absorb water, but they do not dissolve in it. They just become sticky or wet. But concave absorb water and dilute itself in it. Don't forget that's also an hygroscopic salt. Then efflorescence, this one doesn't absorb water. They lose their water crystallization to the atmosphere whenever they are exposed. I hope you understand that. Now, let's look at drying agents before we leave. Drying agents are substances that have affinity for water. I've told you that. Mostly hygroscopic. They have strong tendency for water, so they absorb moisture in the environment that they are. So any environment where there is drying agent, you don't normally see water vapor inside the air. They will have absorbed the water vapor inside the air. So these drying agents are used for drying gases in the laboratory. Now there's a difference between drying agents and desiccants. Desiccants are actually drying agents. Is that okay? But not all dry agents are desiccants. Desiccants are solids. They are substances, or they are solid substances rather, that is placed in a desiccator for drying substances. Now, you don't use them to dry gas inside the desiccator. Desiccants, you don't put gas inside the desiccator. So desiccants are substances placed in the desiccator to dry solids. Is that okay? They are placed in the desiccator to dry solids. That is the function of desiccants. But drying agents, generally, they don't only dry solid, they can also dry gases. Are we together? So drying agents are substances that absorb moisture from the atmosphere, or that have a strong tendency to absorb moisture from the atmosphere. They can dry solid, they can dry gases majorly. They are majorly used for drying gases. But desiccants, they are used for drying solid that you place inside the desiccator. Themselves, they are solid. Is that okay? They are solid. You place them in a desiccator, then they will dry any solid inside the desiccator, because they will provide a dry environment, a dry atmosphere in the desiccator. So that's desiccant. But drying agents can dry both solid and can dry gases. So that's why all desiccants are drying agents, but not all drying agents are desiccants. There are some drying agents that are not desiccants, like conc H2SO4. That one is not a desiccant because you don't put it inside the desiccator. It's a liquid. So, but talking about silica gel. Silica gel is a desiccant and can also be used to dry gases. Now, take note of this important paragraph. I said a drying agent cannot be used if that drying agent reacts with the substance you want to dry. For example, now, H2SO4 is an acid, don't forget. Ammonia is a base. You cannot use conc H2SO4 to dry ammonia gas. It is very, very, it will not work. The reason is because both of them will react together. So you will not use a drying agent. You will not use a drying agent to dry another gas if the gas will eventually react to the drying agent. So for example, I've given you the reason. I've said that H2SO4 cannot be used to dry ammonia because it will react with the ammonia to form a salt. You can guess what type of what will be the name of the salt that will be formed. Ammonia and H2SO4. So it's from ammonium sulfate, which is used as fertilizers. So you don't dry ammonia with conc H2SO4. Now, apart from that, calcium oxide can also not be used to dry hydrogen chloride gas. HCl is a gas. You cannot dry it with calcium oxide because they will react with each other. So take note of that. So a drying agent will be unsuitable if it's going to react with the gas you want to use it to dry. Do not forget. So finally, before we finish our topic on salts, we talk about the uses of salts. What are the uses of salts? Number one, sodium chloride is used for preserving food. Sodium chloride is used in glazing of pottery. Don't forget, we asked you use of this salt. NaCl is used for stabilizing muddy road. Do you remember I once taught you something that in temperate environment they normally have ice. They normally have ice on the road, and to make the ice melt quickly, you sprinkle salt, NaCl, on that ice. Do you remember that? So that's one of the functions of sodium chloride, to stabilize icy road or to stabilize muddy road. Is used in glazing of pottery. That is, when those who are making mud pots and all that, to make the back to become shiny. You rub it with sodium chloride. So you say it's used in glazing of pottery. I hope you are enjoying the view of your school. I'm actually in your floor. This is one floor. So it's used in glazing of pottery. That's NaCl. Now, it's also used in preserving food. In the olden days, if you listen to Pastor's message today, in the olden days, NaCl is used to prevent food from actually decaying or decomposing, and people still use it today. They will just put their fish or their whatever, they will put it inside sodium chloride, and then it will not get destroyed. There's something called locust beans. I don't know if you know locust beans. Locust beans is iru in Yoruba land. You preserve locust beans with salt so that it will not get destroyed. So you preserve food with sodium chloride. Very, very important. So finally, about sodium chloride. Sodium chloride is used during the manufacture of soap. It is used to separate soap from glycerin. It's called salting out. You can sort out the soap. That is, when you add sodium chloride into the soap, then the soap will separate from glycerol. That is called sorting out under soap making. So these are the functions of sodium chloride. Just one out of the many salts that we have in this world. Now let's talk about another example. Calcium carbonate, calcium hydrocarbonate 4 is used for neutralizing stomach acidity. Those having ulcer, so they use something called mixed mag. Some of them contain calcium carbonate, some contain magnesium hydroxide. We have done that one on that base. So is this for neutralizing soil acidity? Fused calcium chloride is used as antifreeze. That is added to car radiator to prevent the water inside from freezing early. Because if water freezes inside your radiator, you have jet gbese. so it's used to prevent car radiator from freezing. So you call it antifreeze. So calcium chloride is called antifreeze. Then remember that calcium chloride is also a deliquescent substance. Remember poso hydroxide ficamachloride. So that card is calcium chloride. So it's also used as drying agent. It's as drying agent. So apart from used as antifreeze, can be used as drying agent. Now zinc chloride is used in petroleum refining. Potassium nitrate is used for making gunpowder. You should remember that in your first term SS1, when we talk about making of gunpowder, you use potassium triazonitrate 5 to make gunpowder. Then it's also used as soil fertilizer. NPK fertilizer uses that NPK means nitrogen, phosphorus, and potassium. So the potassium there can be obtained from KNO3. So don't forget about that. So I've told you 2 uses of KNO3. Then magnesium tetrasulfate 6 is used as laxative or purgative. If you want to go to the toilet and your shit is not coming out, you just take Andrew liver salt. Andrew liver salt contains magnesium sulfate. So it makes you purge. That's what we call purgative. It is as purgative. You purge very well. Or as laxative or purgative. So MgSO4 is used for that purpose. Then copper sulfate is used in dyeing and calico printing. It is used in printing and then is used for dyeing. It's for making dyes. So that's version of copper 2 tetrasulfate 6. Any question? No question. All right, let's continue with use of salts. Sodium carbonate 10 of water. I told you it's called washing soda. Don't forget, calcium oxide is quick lime. Calcium hydroxide is slaked lime. Sodium hydroxide is what? Caustic soda. Now, sodium triazocarbonate 410 of water is called washing soda. The soap is called washing soda. So that's 10 of water. It's not really soap like that, but it's a form of soap. It's called washing soda. So it is used in softening of water. We will see that in our next topic. That's our next topic, water. You can soften water with washing soda. Now, calcium chloride is used as drying agent. I've already told you that because it's deliquescent. Ammonium chloride is used as washing powder. And ammonium chloride is also used as electrolyte in dry cells. We'll see electrolyte in dry cell when we get to electrolysis very, very soon. Calcium sulfate, that's calcium tetrasulfate 6, is used for making plaster of Paris, POP. When you play football and then you break your hand, they put POP on your hand. That POP is made from calcium sulfate, calcium tetrasulfate 6. So these are the functions of salts that are very important in our society, and this is the end of salts. So do well to hear this video very well. If you have any question, ask me question. Voice note me on WhatsApp. You have my number, or chat me up, and I will answer your question gladly. I wish you best of luck. Try and attempt my test, chemistry test 9. It's going to be it will be based on what you have done on acid, bases, and salts. So that test promised to be interesting and all that. God bless you. We'll meet in our next class on water. Water is week 6. Water is week 6. Yeah, water is week 6. Water is week 6 or week 5. Anyhow. Alright. Bye-bye, everybody. So I'm in Science B. This is Science B. Chidera, can you see your class? Alright. So, thank you.